Welcome to The Explainer. Today, we are tackling a physics puzzle that, honestly, it kind of challenges something you probably think is just common sense. We're talking about a paradox that completely flips things on their head.
All right, let's just dive right in with a question. And look, the answer probably seems super obvious. Which is more elastic, a steel beam or a rubber band? Go on, take a second. What does your gut tell you?
Yeah, I'm willing to bet that almost everyone, myself included at first, would say the rubber band, right? I mean, it stretches, it's flexible, that's what elastic means, isn't it? Well, here's the thing. Physics has a very different and way more surprising answer for us.
Okay, so to really get this, we have to basically throw out our everyday definition of elastic. See, in physics, it has almost nothing to do with how much something can stretch. Nope. It's all about the snapback. It's a measure of how fiercely an object resists being changed and how perfectly it bounces back to its original shape.
So, at the very heart of all this are these two opposing forces. They're always in a tug-of-war anytime you try to change the shape of a solid object. Let's break those down.
So you've got two key players here. First, there's the deforming force. That's you, right? Pushing or pulling on something. But fighting back against you is the restoring force. This is the object's own internal, well, you could call it a desire, to get back to the way it was. It's that powerful snapback.
And how a material handles this little battle is what makes it either elastic or plastic. It's pretty simple when you think about it. An elastic material, like a good spring, has a huge restoring force. It fights like crazy to get back to its original shape. But then you have something plastic, like, say, a lump of clay. It has a really weak restoring force. You squish it, and it just kind of goes, yeah, okay, I'll stay like this. No fight at all.
Okay, so to really compare something like steel and rubber, physicists can't just use words like stretchy or bendy. That's not precise enough. They need a proper language, a way to measure this constant push and pull. So let's learn a couple of key terms. First up is a word you know, but with a specific physics meaning: stress. Think of it like a standardized version of pressure. It's the force you're applying, but spread out over a specific area. So the formula is just force divided by area. Simple enough, right?
And when you apply that stress to an object, the result, the actual change in shape, is called strain. Strain is just a measurement of how much the object deformed compared to how big it was to begin with. It's just a ratio, the change in length divided by the original length. That means it doesn't even have any units.
So, we've got stress, the force we apply, and strain, the deformation that happens. Now here's where it gets really cool. These two things are connected by a really fundamental law of physics. We got to go way back to the 17th century for this one. A brilliant scientist, Robert Hooke, he figured out this super simple but really profound relationship between the pull you put on something and how much it actually stretches. So, using the words we just learned, what Hooke's law says is this. For any elastic material, as long as you don't break it, the stress you apply is directly proportional to the strain you get. It's a perfect one-to-one relationship. More stress, more strain. Beautifully simple.
This perfect relationship gives us one single, incredibly powerful number, the modulus of elasticity. You can just think of it as a material's stiffness rating. It tells you exactly how much that material resists being deformed. A super high modulus means you have to apply a ton of stress just to get a tiny little bit of strain. And this one number, this is the key to our whole paradox.
All right, we've got our physics toolkit ready. We understand stress, we understand strain, and we have this crucial number, the modulus of elasticity. It's time. Let's go back and finally solve this thing.
So let's ask the question one last time, but now with our new physics definition in mind. Which one is truly more elastic, steel or a rubber band? Which one fights harder to get back to its original shape?
And this chart just lays it all out. The answer is in the numbers, and wow, it's not even a contest. The modulus of elasticity for steel is around 200 gigapascals, and for rubber, it's 0.01. I mean, we're talking about a difference of thousands of times. It's absolutely huge.
So what does that massive number for steel actually mean? It means steel has an unbelievably powerful restoring force. It resists being changed way more than rubber does. To get even a tiny stretch out of steel, you need a huge force, and that steel is using an equally huge force to snap back. And that powerful snapback is the true measure of elasticity in physics. The answer is steel. Steel is vastly more elastic than rubber. Now, this is more than just a fun little physics riddle to stump your friends with. This principle is absolutely fundamental to, well, pretty much the entire modern world we've built.
I mean, think about it. This is everything for engineers. It's how they design a bridge that can flex with the weight of traffic but always snap back, never permanently sagging. It's how they build machine components that can take on constant stress without breaking down. It's what makes the cables in an elevator or a crane strong and reliable enough to lift insane amounts of weight over and over and over again. So here's the big takeaway. Our everyday intuition, what feels right, can sometimes be totally misleading when it comes to science. For elasticity, it's not about the stretch, it's all about the strength of the return. And that really makes you wonder, doesn't it? What other basic ideas about the world do we have completely backwards?